we had already covered the sixth session wherein we have finished the chapter called chemical bonding. Okay, we have finished that chapter. Now we are moving towards the next chapter, and the next chapter in our section is redox reactions. Okay, redox reactions is our next chapter. That is what we're gonna cover. Okay, let me welcome you all. Hi, Johan. Very good evening. Okay, chalo, let's begin. Redox reaction. Now, what is mean by redox reaction? You can clearly see here with the names. Red ox. That doesn't mean red color ox or something like that. Red means this red part comes from the reduction. OX comes from the oxidation. So that is how the oxidation and reduction. Basically, redox means oxidation and reduction. And both these process generally happens hand in hand. Hi Rahul, have a very good evening. So generally the oxidation and reduction happens hand in hand. That is why they have been together named as red ox. Okay. So what is the basic difference? What is the basic difference between oxidation and reduction? See, oxidation. Oxidation, you can see the word itself is there, oxy, right? And you also have an oxy word in oxygen. Right? Now, obviously, in oxygen, you have OXY. Here, you have a OXY. That is obviously because of English. But, anyways, so oxidation, that means what? Something which is getting added to the oxygen. Something which is getting added to oxygen would be termed as a oxidation. And that is why the addition of oxygen would be called as oxidation. For example, you can clearly see here the magnesium. Magnesium is getting added to oxygen to gives you MgO, magnesium oxide. That means magnesium has been oxidized. Similarly, if the hydrogen is getting added to the oxygen, you get the H2O. So here your hydrogen has been oxidized because it has got added to the oxygen. So something which has got added to the oxygen would get oxidized, obviously. Now, what is opposite of it? Reduction. If the addition of oxygen is oxidation, what would be its opposite? Its opposite would be removal of oxygen. So removal of oxygen would be termed as the oxidation. For example, here your copper was with the oxygen CuO. So when it is added to copper carbon, you got Cu and oxygen has got away from the copper. That means your copper has got reduced here. Okay. So basically, addition of oxygen will be termed as oxidation. Removal of oxygen is called as reduction. Now, the next definition. Now, whatever definition we had seen, that is from the perspective of oxygen. Now, let's see how it is from the perspective of hydrogen. Now, see, whether if you perform oxidation or reduction, there would always be a concern of either oxygen or hydrogen. That is why this oxidation reduction reaction is also there from the perspective of hydrogen. So if the addition of oxygen is oxidation, the addition of hydrogen would be termed as reduction. If the addition of oxygen is oxidation, then addition of hydrogen is what? Reduction. It is exactly opposite. See, if the addition of oxygen is oxidation, then removal of hydrogen. Removal of hydrogen would be called as oxidation. For example, H2S reacts with Cl2 to give you HCl, okay, and you get the sulfur. So basically, sulfur's hydrogen has gone with the chlorine. Sulfur's hydrogen has gone with the chlorine, and sulfur now came out without any hydrogen. What does that mean? That means sulfur has been oxidized. The sulfur has been oxidized. Similarly, here, sulfur combines with hydrogen to give you H2. That means the hydrogen has got added to the sulfur. Then what do you call this as? Reduction. That means sulfur has got reduced here. Another definition, increase in positive charge. See, there's one more definition of oxidation, that is loss of electron. Loss of electron is oxidation, and gain of electron is called as reduction. Gain of electron is reduction, loss of electron is oxidation. So Fe plus 2. If you look at the oxidation number of iron, oxidation number, atomic number of iron is how much? It's 26. So 26 iron, neutral Fe would have 26 electrons, right? Now when you have Fe plus 2, that means you will have a 24 electrons here. And Fe plus 3. Fe plus 3 means it has got 3 electron less. So Fe plus 3 is what? 26 minus 3. That means 23 electrons. So your iron went from 24 electrons to 23 electrons. That means what? That means your iron has lost an electron. That is why Fe plus 2 is said to be oxidized. That is why loss of electron is also called as oxidation. If you look at this reaction in a reverse direction, it seems like it is a reduction, and it is reduction. Fe plus 3, as we had seen here, Fe plus 3 has how many electrons? 23 electrons. And Fe plus 2 has how many? 24 electrons. So Fe plus 3 has gone from 23 to 24 in Fe plus 2. That means it has gained 1 electron. That is why the gain of electron will be called as reduction. Loss of electron is called as oxidation. Similarly, oxidation number. See, increase in positive charge. Whenever your positive charge increases, it will be oxidation. Whenever your positive charge decreases, it will be called as reduction. Basically, reduction is the English word, you know that. So what is getting reduced? The oxidation number is getting reduced. So whenever you will see this increase and decrease, this might confuse you a bit. So let me give you a simple solution. You know what? You might get confused with the meaning of oxidation, but you will not get confused with the meaning of reduction. We know what is meant by reduction, right? Reduction means something getting decreased. So what is getting decreased here? The oxidation number. The oxidation number is getting decreased. You can see here, Fe went from plus 3 to plus 2. So this oxidation number has got reduced. So whenever you will see oxidation number getting reduced, it's a reduction for sure. And obviously, to its opposite, that means increase in oxidation number would obviously what? Oxidation. And so on. That is how oxidation reduction. Yes, Snake Ambu Chelvan, you have one doubt. I hope that is not your name, right? What's your doubt? Snake Ambu Chelvan. Yeah. You wanted to ask me something, right? You can ask me. Okay, anyways, it seems you're not. Anyways, chalo, moving ahead. So I hope this must have been clear to you. If you have any doubt, you can ask me again or later on also, no problem with that. But for the time being, I'll move ahead. Yeah. So continuing with the oxidation and reduction. Oxidation. Again, as I told you, increase in oxidation number. The tin's oxidation number is plus 2 here. It went from plus 2 to plus 4. Right? Similarly, manganese oxidation number you can see clearly plus 7. From there it went to plus 2. So what is getting decreased? Oxidation number is getting decreased in reduction, and oxidation number is getting increased in oxidation. And lastly, again, the removal of electron. Removal of electron or loss of electron would obviously be your oxidation, and addition of electron would be your reduction. So that is what. So these are some of the ways by which you can differentiate between oxidation and reduction, or you can also identify if the given reaction is oxidation or not, or if it is reduction or not. Okay, that is what is all about for oxidation and reduction. Okay, moving ahead. I was keep talking about oxidation number, right? So what is your oxidation number? See, it's an imaginary or apparent charge. It's imaginary. Obviously, it's imaginary because we as a, I would say, scientist or student or learner, we have give that number. See, Fe plus 3, there is nothing like plus 3 or plus 2. Okay. Fe plus 3 is a species which has 3 electrons less than neutral Fe. That is what Fe plus 3 is. Basically, it's a cation. Or Fe plus 2 is a species which has 2 electrons less than the normal Fe. That is also cation. So that plus 2 and plus 3 is an imaginary or apparent charge which we had denoted over the head of the given atom for us to understand it in a clear way, whether what kind of properties it might display or what kind of reaction it might show. It's all for that. Okay, that is why it's an imaginary or apparent charge gained by an element when it goes from its elemental free state to combined state in a molecule, which obviously happens. See, let me give you one reaction. See, whenever you have any element, metal, non-metal, or anything, if it is uncombined state, the oxidation number also indicates whether you have your atom have been attached to more electronegative atom or a less electronegative atom, or is it a free atom or element. So oxidation number basically indicates whether you have been attached to more electronegative atom or less electronegative atom. Okay, the all basis goes in that. So if you see the reaction between hydrogen and oxygen, see 2H2 combines with O2 to give you 2H2. So if you write this reaction, see oxidation number, if I write oxidation number of oxygen hydrogen, for hydrogen it's 0, for oxygen also it's 0. But when it gets combined, the oxidation number of oxygen atom is -2. And for the hydrogen it's +1. 2 hydrogen, each in +1, +1 into 2 it becomes +2, and oxygen is -2. So -2 plus 2 is 0. Okay, generally molecule has no charge, 0. It is like this. I'm saying generally molecules has no charge. Yeah, salts will have definitely charge. So you can see that. So this oxidation number comes on the hydrogen, indicating that it is attached with the more electronegative element. And oxygen is getting a -2 charge, indicating that oxygen is attached to less electronegative element. Okay, so it all goes like that. Okay, moving ahead, it's a relative charge. It's a relative charge in a particular bonded state. What is mean by relative charge? Relative charge means, let me tell you one thing. See, if you write the structure of PCl3 here phosphorus is in a +3 and each chlorine is in a -1. So 3 chlorine together become -3 and phosphorus +3 becomes 0. So here chlorine is in -1, phosphorus is in +3. But if you bond same chlorine to the oxygen here, then your chlorine has a +1, +1, +1. So 2 chlorines it become +2, oxygen it become -2. So did you understand now? Oxidation number is not something which is constant. Oxidation number is not something which is constant. It changes from a compound to compound. Okay, and it also depends whether your atom or element is it attached to more electronegative element, less electronegative element, or is it attached to the same atom. If it is attached to same atom, obviously oxidation number would be 0. Okay, so it all lies on the electronegativity factor and electronegativity factor only. So the chlorine which has oxidation number -1 in PCl3, same chlorine has oxidation number +1 in OCl. So from that you must have understood that this oxidation number is nothing but a relative charge in a particular bonded state. Okay, chalo, you haven't asked me the doubt, snake, Ambuchelvan, but anyways, moving ahead. See the rules. Rules governing oxidation number. What are some of the rules? How can we find out whether what is the oxidation number of given element? Because till now you can clearly see I'm immediately finding out the oxidation number of chlorine, phosphorus, hydrogen, oxygen. That might make you wonder that how am I able to do this? You will also be able to do this once you come to know all the rules. Okay, so what are the basis of this rule? As I told you already, it's been written here also. The basis of these rules, which rules? The rules which will help you to find out the oxidation number. The basis of all these rule is the electronegativity. Electronegativity is the most important basis for finding out the oxidation number. Okay, so let's move ahead now. Yeah, first, the fluorine atom. Fluorine atom, I call fluorine as a king of electronegativity. It is a king of electronegativity in periodic table. Okay, it's a king. Why it is king? Because it is the most electronegative element in the periodic table. It is the most electronegative element in the periodic table. You will never find fluorine atom going in a +1. Never. It never goes in a +1. Yes. Again, it is a chemistry. Yeah. So you will have some exceptions. Okay. But those exceptions and those, anomalies, you will find in the cases which you will not encounter in a regular reactions or in your JEE or NEET syllabus. Okay, it is in the advanced syllabus, but then also you will not find fluorine going in a +1 quite oftenly. It's very rare case. Okay, so for our syllabus being, as far as the syllabus is concerned, let's consider fluorine never goes in +1. Why? Because it is the most electronegative element till now. Its electronegativity, I guess maybe I have told you the electronegativities of different element. Once we start the organic, you will come to know. Okay, but for the time being, the electronegativity of fluorine is 4. Okay, it always has oxidation number equal to -1 in its compound. See, whatever compound you take, you will always find fluorine as in -1. You will never see fluorine as a even -2. It never goes to -2. It never goes to +1, +2. You will find it as a 0, 0 in a F2 molecule, obviously, because it is attached to itself. It is attached to itself, so it is obviously 0. But in every other compound with every other element, it will always be -1. Okay, next, the queen of oxygen atom. Queen by that sense, I does not mean oxygen is a wife of fluorine, but oxygen's electronegativity is 3.5. So it's the second most electronegative element. So by that you must have understood oxygen will also be never be in -1 or -2, whatever. It only goes in sorry, my bad. Oxygen also always goes in minus oxidation state. You will not find oxygen going in plus oxidation state. It goes in plus oxidation state only and only with the fluorine. With fluorine, because fluorine is more electronegative than oxygen, then obviously oxygen will go in a plus oxidation state there. But otherwise, no. Otherwise, oxygen's oxidation state will change. It will go from -1/3 to -1 to -2. Yes, it will change, but it will be minus only. It will never be plus. Okay. So, in general, as well as in its oxides, oxygen atom has oxidation number equal to -1. Yeah, but yes, it does changes. Okay, you will come to know that later on. We will see about that also. See, in peroxides, oxygen's oxidation number is -1. Why? Let me write the structure of peroxide for you. H2O2. So this is the structure of peroxide. Hydrogen. It is like a spectacle kept on the table. It looks like that. Okay. Now you got two hydrogen, right? Each hydrogen. This hydrogen is +1. This hydrogen is a +1. Right? So apart from oxygen you got +2. So apart from oxygen, if you have got +2, that means oxygen must have -2 charge, right? But there are two oxygen atoms, no? The two oxygen atom has a -2 charge. That means single oxygen atom has a -1 charge. That is why, and that is how in peroxides you will have oxygen in the -1 oxidation state. Same is the case with the sodium peroxide also. Okay. Then superoxide. See, in superoxide, KO2. Now potassium is a alkali metal. Potassium is a alkali metal, and alkali metal will always have, potassium is an alkali metal, and alkali metal's oxidation state is always, mark my words, I mean always is +1, because they have only one electron extra than their noble gas core. So even if they lose that one electron, they will have noble gas core. That is why they loses only one electron to get oxidation state +1. Since it is always, that is why I'm saying. So if the potassium is in +1, that means that there is a -1 charge on the oxygen, right? Because you can see the overall charge is 0, right? So +1 -1 is equal to 0. That means if the potassium is +1, the remaining two oxygen will obviously have a -1 charge. Since you got two oxygen atom, the -1 would be divided by 2. That is why the charge that you have is minus. Okay. It is only happen with KO2, which is also called as the superoxide. Remember these terms. I'm telling you once again. See, O2 minus is called as oxide. Okay. O2 2 minus is called as peroxide. And lastly, O2 1 minus is called as superoxide. As a student of NEET or JEE, you always need to remember this terminology. It will come handy and useful to you. Okay, O2 minus is oxide, O2 1 minus is superoxide, O2 2 minus is peroxide. Similar thing happened with the KO3. Again in the KO3, as I told you, in KO3, potassium has a +1 charge, right? That means 3 oxygen must be having a -1 charge. So each oxygen will always obviously have a -1/3 charge, right? Lastly, in oxygen fluoride. So as I told you, oxygen goes in a +1 oxidation state only with the fluorine, because fluorine is always in a -1 oxidation state. So here each fluorine is -1. So two fluorine together become -2. That means oxygen obviously have a +2 charge. That is why in OF2 oxygen is in +2, and O2F2 is just like a peroxide only, right? So this is oxygen, fluorine, fluorine. Each fluorine is in a -1, minus. So overall you got a +2 charge. Again the +2 charge gets distributed with the two oxygen atom. Therefore each oxygen atom will have a +1 plus. So it is like that. Okay, I hope this must have been clear to you. Anyone having any doubt, you can ask me in the comment section. Snake seems to forgotten, or maybe he has disappeared anyways. So let's move ahead. Yeah, moving ahead. So here we had seen the how the oxidation number of fluorine atoms and oxygen atoms are. Okay, here hydrogen atom. Now see, hydrogen atom in general, hydrogen atom has oxidation number equal to +1. General. Why? Because if you write the atomic number of hydrogen is 1, right? So you got only 1s1, 2s is 0. So your hydrogen can gain only 1 electron to become 1s2. Okay, in that way it shows -1, and it can lose this electron to become plus. Now obviously again there comes the electronegativity factor. If the element is more electronegative than hydrogen, then hydrogen would be in plus 1. If the hydrogen is with the metals. Now remember one thing. You might have seen in the periodic table, hydrogen being kept just above the alkali metals. You might have seen that. But that is not a real position of hydrogen. See, hydrogen is like a, what should I say? Hydrogen is like a Shiva. Like Shiva, we know as a god, he's present everywhere. But it's just like that. Hydrogen is like a Shiva of the periodic table. He or it is present everywhere. It shows the properties of alkali metal. It shows the properties of D block element. It shows the properties of P block element, and so on. Okay, it shows the properties of A block element also. I will come to that when I teach you the chapter called hydrogen. Okay, but for the time being, hydrogen might have been kept just above the alkali metal, but it is not alkali metal. It's the real position. It's the real position. If you go by electronegativity, is in the P block, because hydrogen's electronegativity is 2.43, and you know carbon is a non-metal, right? Carbon's electronegativity is 2.50 and hydrogen's is 2.43. So you must have understood by this figure that how much non-metallic hydrogen is. Okay. Only thing is that if it is getting attached with a more electronegative atom than it, for example, oxygen, fluorine, halides, carbon, then your hydrogen will be in the plus one. But whenever it is with the metals, that means metallic hydride, it will be in a minus, because obviously lithium, sodium, potassium, their electronegativity lies somewhere around 1 only. So electronegativity is 1, hydrogen's electronegativity is 2.43. You must have got how much gap is that? That is 1.43 is too much. You know what, for an any compound to have ionic character, the electronegativity difference of 0.2 or 0.3 is fair enough. It is too much. 1.43, oh, that's too much. That's the difference between carbon and fluorine. That is why with the metals, hydrogen is present at hydrides. Now you can see the name is ID is given. The ID name means negative charge. Okay, whenever any species having a negative ID word or ID, what I would say, it's a subscript, ID subscript after its name, that means it must be having a negative charge. If any substance is having a IUM, that means it's a positive charge. It's a positive charge. You must have understood from that by the name called sodium, IUM, potassium, rubidium, cesium. Take all the metals. Metals always, the name of metals will always end up with the IUM because they can form positive charge very easily. Okay. So IUM for positive charge, ID for the negative charge. Okay. And ATE for the negative charge again. Let me tell you one more. SO4 2 minus. We call SO4 2 minus as sulfate. So you are adding ATE subscript. Okay. Then you have NO3 1 minus. Nitrate. Again ATE. So whenever you have ATE subscript, that means there is a negative charge and it's a polyatomic species. Okay. Whereas this IUM, sorry, not polyatomic, it's polyatomic negatively charged species. Or if you have a monoatomic positively charged species, you have IUM. Okay. But anyways, we will come to know, we will come to that later on in a terminology sector. Okay. But right now, hydrogen, if it is with the metals, it is in -1. If it is with any other element, it will be in +1. Okay. In general, all halogen atoms. Now this is for the halogen atom. All halogen atom, which is chlorine, bromine, iodine, have oxidation number equal to -1. I forgot to mention fluorine also here. Fluorine is always in a -1, you know that. So fluorine, chlorine, bromine, iodine, each one of them has -1 oxidation state. That's for sure. Okay, but apart from that, if your halogen is attached to more electronegative element, for example, with the oxygen, if you're, no, I'm not talking about fluorine, I'm talking about chlorine, bromine, iodine, because oxygen is more electronegative than Chlorine, bromine, and iodine, not fluorine. So if your chlorine, bromine, or iodine, if they are attached to the more electronegative element, then they might have a plus oxidation state. For example, if, as I written here, if halogen atom is attached to more electronegative atom than itself, then they might show positive oxidation state. For example, chlorine is showing a plus 5 oxidation state here in KClO3. Iodine is showing plus 5 oxidation state in HiO3. Chlorine is showing plus 7 oxidation state in HClO4. And bromine is showing plus 5 in KBr. Okay, how it is showing plus 7 and plus 5, we will see that very shortly, where you will understand how to find the oxidation number of a given element. Okay, sure. Moving ahead, metals. So alkali metals, as I told you earlier, alkali metals: lithium, sodium, potassium, rubidium, cesium, and francium also. Okay, where francium we don't form that many compounds with, but yes, since it's an alkali metal, it is unfair to, unfair to ostracize this. So I included here lithium, sodium, potassium, rubidium, cesium, francium. Always have oxidation number +1. You will never find them having any other oxidation state than +1, because technically that is not possible. Technically that is not possible. That is why. Similarly, alkaline earth metals. Alkaline earth metal like beryllium, magnesium, calcium, strontium, barium, and lastly radium. Each one of them always have oxidation number +2. They will also have +2 oxidation state always, just like their brothers alkali metals. Why I'm saying brother? Because both of them are H block element. H block has been divided into two groups. One is alkali metal, another is alkaline earth. That is what your H block is. Okay. Now the note. See, metal may have negative or zero oxidation number. Metal might have a negative oxidation number also. You till now you have seen metal having positive oxidation number only. In this case, it's a positive. If your metal is what is uncombined, if your metal is uncombined with any other atom or element, obviously its oxidation number is 0. Zero oxidation number is the only oxidation number which is shown by every element in the periodic table, and there is no surprise to it. If you are not combined with any other element, why would you have electron being lost or gained, right? Then obviously your oxidation number has to be 0, right? But there are some cases where metal might have a negative oxidation state. Okay, but those cases we will see whenever the example comes. Okay, right now let's keep it there only. Now this thing, always remember this thing: aluminium. Aluminium has +3 oxidation state always. Always means always. You will never find aluminum having any other oxidation state. Okay, it is one of those elements. It is just like what I would say. It is just like a fluorine, which will not show any other oxidation state, or just like alkali metals. Okay. Next, oxidation number of an element in a free state. Free state means what? Uncombined state. Free state means your uncombined state. So oxidation number of element in a free state or in allotropic forms is always 0. Allotropic forms means what? It's existence of a same element in a different form. For example, carbon. You know that carbon exists as a diamond, as a graphite, as a fluorine, or as a, it isn't called as smoke as said, but you can say char. You might have seen char being accumulated over the sides of the flame of the chimney. I don't know. I wonder if you have seen chimney or not. But anyways, this diamond, graphite, fluorine, all of these are the allotropes of carbon. And in all those states, the oxidation number of carbon would be 0 only. Okay, so these are the allotropes of oxygen. Oxygen is O2 and O3. In both cases, oxidation number of oxygen is 0. S8 is the allotrope of sulfur. P4 is the allotrope of phosphorus. In all those cases, forget about this allotrope and all that. If your atom or element, if it is not combined with any other atom or element, obviously its oxidation number has to be 0. Okay, it is simple thing. Why? Because when it is not combined with any other atom, then the electronegativity difference would be 0. If that difference is 0, obviously there is no drifting, donation, receiving of any electron density. When that happens, why would you have a -1 +1 oxidation state, right? Yeah. Chalo. Moving ahead. Next, some of the helpful rules for you to find it out. What are these helpful rules? The sum of charges of all the elements in a molecule is always 0. If you take any molecule for that matter, take CO2, H2S, CH4, C2H6, H2O, take any molecule, whatever you want. You will always find the sum of charges, or I would say oxidation number. The sum of oxidation number of all the elements in the molecule is always 0, because naturally every molecule tends to be neutral. Neutral is the stability. That is why we also want to be neutral, right? You will never want to be in a state of hyperactive or hypoactive. You want to be somewhere in the middle, normally active, right? So sum of the charges of all the elements in an ion, mark my words, here I was talking about sum of charges of elements in a molecule is 0. I'm talking about molecule. Here the sum of charges or sum of oxidation number, here charges mean oxidation number, okay? The sum of charges or sum of oxidation number of all the elements in an ions is equal to the charge on the ion. For example, let's take this SO4 2 minus. Now in SO4 2 minus, the oxidation state of sulfur is, it's a +6. Oxidation state of oxygen is -2. You got how many oxygen? 4. So -2 into 4, it become -8. So +6 -8 is equal to -2. You can already see -2 charge is on the ion already, right? That is why, or that is how the sum of oxidation number of all the atoms or elements in an ion is equal to charge on the ion. Okay. Secondly, if the group number of an element in a periodic table is n, if the group number of element in the periodic table is n, then its oxidation number may vary from n to n minus 8. Sorry, if the group number of element in the periodic table is n, then its oxidation number may vary from n to n minus 8. But it is mainly applicable in a p block element. It is mainly applicable to p block element. Okay, let's see the example of nitrogen. See, nitrogen belongs to the 5th group in the periodic table. Nitrogen belongs to 5th group in the periodic table. Therefore, as per the rule, n to n minus, right? That means 5 to 5 minus 8. Now 5 minus 8 is equal to how much? -3. Therefore, nitrogen shows oxidation state from -3 to +5. It is not applicable everywhere, okay? See, oxygen belongs to the 6th group. Then oxidation state of oxygen has to be 6 to 6 minus 8. That means 6 minus 8 is how much? 6 minus 8 is -2. So -2 to +6. Now oxygen does not show +6 oxidation state. Yeah, it does show -2. That is why I'm saying it is applicable to Most of the p block element, yeah, but not the second period. Nitrogen, oxygen, fluorine, this comes to the second period. If you are talking about third period, that means sulfur, phosphorus, yes, it is applicable. Okay. Now, as far as nitrogen, oxygen, fluorine group is concerned, this rule, what rule? That the oxidation number of an element goes from n to n minus 8, where n is its group number. Okay, it is not applicable to fluorine, oxygen, carbon. It is applicable to nitrogen. However, I'll show you how. See, -3 oxidation state of nitrogen is shown by nitrogen in ammonia. Here nitrogen is in -3. Then you have a -2, N2H4. N2H4 nitrogen is in a -2. Then you have NH2OH. In NH2OH, your nitrogen is in a -1 oxidation state. Sorry, -3, -2, -1, 0. 0 is obviously shown by N2. Nitrogen gas will always be in a 0 oxidation state. Then +1. +1 is shown by N2O. Because oxygen is in a -2. So 2 nitrogen will have a +2. And each nitrogen atom will have a +1. +2 nitrogen shows in NO. In NO it shows +2. In in N2O3 it shows +3. N2O4, sorry, I wrote 5 by mistake. N2O4 it shows +4, and +5 is shown by nitrogen in N2O5. In N2O5 it is in +5. So these are some of the oxidation states of nitrogen. Obviously we will cover that in a chapter called p block element. Okay, but for the time being, that's how it is. Okay, chalo, moving ahead with this now. Let's see how can we calculate the average oxidation number. How can we calculate the average oxidation number? You will come to know shortly why I'm saying average oxidation number. Okay, now you can see the undermark. Undermark is for the sulfur here, right? H2O3. Now we don't know the oxidation state of sulfur here, right? But as a rule, the rule which we saw just now, where we came to know the oxidation number of sodium as well as oxygen, right? So let's take it here. Na2S2O3. We need to find out for sulfur, right? For nitrogen, it's a +1, right? There are 2 sodium. Sorry, why I'm saying nitrogen? Sodium. For sodium, it's a +1. You got 2 sodium, +1 into 2. Sulfur, we don't know. So let's write 2x, right? Each oxygen, you have a -2. -2 into 3. This overall is equal to how much? 0. Because do you have any charge on a molecule? No, right? There is no charge here. So what would it be? +2 plus 2x -2 into 3 become -6 is equal to 0. So 2x minus 4 is equal to 0. Therefore 2x is equal to 4 and x is equal to 2. Which 2? +2. So +2 is the average oxidation number of sulfur here. Okay, you can see that here, but if you look at the reality, it is not like that. It is not like that. It is something different. Let me show you how Na2S2O3. That means when I'm saying average oxidation state, it is the sum. It is the sum of oxidation number of both the sulfur atoms. So the sum comes out to be +2. But that does not mean that both the sulfur are in +2. This +2 might have come then also when you have both sulfur in +2, yeah. But it will also come when you have one sulfur in +4, another in 0, right? Because +4 plus 0 divided by 2 is also equal to +2. That is what the case is here. See, let me write the structure for you. The structure is like this. S double bond O, O minus Na plus, O minus Na plus, and it is doubly bonded to its brother, which is sulfur. So if you write the oxidation state of this sulfur, it is +4. And for the oxidation state of this sulfur has to be 0. Why it is 0? Because it is bonded to another sulfur only, no? It is not bonded to any other element which is more electronegative than it. It is bonded with itself. That is why this sulfur is in +4, this sulfur is in 0. That is why their average oxidation number comes out to be +2. So average oxidation number might mislead you. Okay, but anyways, nonetheless, it always gives you the exact oxidation number. Next is Na2S4O6. The underline is for the S4. Let's find out what is the oxidation number of sulfur here. Again, 2 sodium, you got +1 into 2. You haven't asked me that doubt. It's like you have said it thrice. One doubt, one doubt. What is your doubt? You can ask me, no? You haven't asked me, Snake. So +1 into 2. Plus you got 4 sulfur, right? So 4 sulfur, let's write it 4x plus 6 oxygen atom. So -2 into 6. Charge again is 0. So you got +2 plus 4x -2 into 6, it becomes -12, 0. +2 minus 12, 4x minus 10 is equal to 0. 4x is equal to 10. And therefore, x is equal to 10 divided by 4, which is equal to 2.5. So 2.5 is your average oxidation state for sulfur. But again the question comes, is it the real oxidation number? I mean, is each sulfur is in a 2.5 oxidation number? No. You cannot have, let me hear out once again, you cannot have a fractional oxidation number in any molecule. I mean, yes, oxygen does have -1/3 and all that there, but as a single atom, if you're talking about single atom, no, it will not, you will not see that. So how it is this? How it came out to be 2.5? Let's find out its structure. Its structure will help you understand how it is like that. See, S double bond O, S double bond O, O minus Na plus, okay, then sulfur, 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 double bond O, double bond O, O minus Na plus. So you can look at here, this terminal sulfur, they are in a +5 oxidation state. This sulfur also, this sulfur is also in a +5 oxidation state. But these two sulfur are in a 0 oxidation number. So if you add them together, how would it turn out to be? +5 plus 0 plus 0 plus 5, which makes it 10 divided by 4. And that is why you have a 2.5 as an average oxidation number of a sulfur in a Na2S4O6. But if you find it individually, you can see that 2 sulfur atoms are in a +5 each, and other 2 sulfur atoms are in a 0 oxidation number each. Okay. Chalo, moving ahead. I hope this must have been clear to you. If you have any doubt, you can ask me in the comment section. Snake, you haven't asked me the doubt yet, but anyways, I'll move ahead now. Yeah. So let's solve this. Oxidation number. Calculate the oxidation state of all the atoms in the following species. Let's solve it one by one. I have kept the space also for the next slide. Cl minus. Now obviously you need to find out the oxidation number of a chlorine here, not the oxygen, because for the oxygen we knew. So chlorine, it will be X plus minus 2 is equal to minus 1. So x is equal to minus 1 plus 2. So that is why x is equal to plus 1. So plus 1 is the oxidation state of a chlorine in a ClO minus. Okay. Let's solve it for the NO2 1 minus. Again, nitrogen we don't know. Let's take a x plus minus 2 into 2 is equal to minus 1, right? Minus 1 you have for the oxygen. Each oxygen is having a minus 2. Minus 2 into 4, it is x minus 4 is equal to minus 1. So x is equal to minus 1 plus 4. So x is equal to minus 1 plus 4 is equal to plus 3. So plus 3 is the oxidation state of nitrogen in a NO2 1 minus. Similarly, NO3 1 minus. Now I might not have a space, but I'll write the NO3 1 minus here. NO3 1 minus. Again, nitrogen is x. Oxygen is a minus 2 into 3 is equal to minus 1. So x minus 6 is equal to minus 1. X is equal to minus 1 plus 6. 6 minus 1 is equal to plus 5. So you will have a plus 5 oxidation state as in NO3 1 minus. Then let's go for the next CCl4. CCl4, we don't know the oxidation state of carbon. So let's take it 0. Sorry, not 0, X. But for the chlorine, we know, right? Chlorine's oxidation state, if it is bonded with a less electronegative element, and yes, chlorine is a more electronegative than carbon, or in other words, carbon is less electronegative than chlorine. So therefore, you got minus 1 into 4. Charge 0, right? So x minus 4 is equal to 0. Therefore, x is equal to plus 4. So plus 4 is the oxidation state of carbon in a CCl. Right? Let's look at it once again. Okay. So moving ahead. Next are the oxidation states for the chromium and for the manganese that we will solve in the next slide. So K2CrO4. Again, potassium is what? Potassium is alkali metal, right? We knew that alkali metal's oxidation number is a plus 1 into 2 plus X plus oxygen minus 2 into 4 is equal to 0. So you have a plus 2 plus X minus 8 is equal to 0. So you have X minus 6 is equal to 0. And therefore you have X is equal to plus 6. So plus 6 is the oxidation number of a chromium. And the next one was what? Next one was KMnO4. Now KMnO4 again, for potassium you have oxidation number plus 1. We don't know for the manganese. Each time you always need to solve in this way, okay? Oxygen is minus 2 into, you got a 4 oxygen atom. Overall charge is 0 once again. So plus 1 plus X minus 2 into 4 minus 8 is equal to 0. So you got X minus 7 is equal to 0. Therefore, you got X is equal to plus 7. So plus 7 is the oxidation state of a manganese in Km. That is how you can solve the oxidation states for the different elements. Okay. Chalo, moving ahead. Let's take a look at it once again. If you have any doubt, you can ask me in the comment section. Okay, chalo. Next, some miscellaneous examples. Why I'm saying miscellaneous examples? because you will have exceptions here. You will have exceptions. So if I ask you to find out this bluely colored element's oxidation state, the bluely colored element oxidation state, that means the chromium here in CrO5. So if I ask you to find out, let's solve it first of all. It will be x plus, you got minus 2 into 5, right? There are 5 oxygen atoms. Number 0. So it will become x minus 10 is equal to 0. Therefore, x is equal to plus 10. Now, as soon as you get the plus 10 answer, the tube should be, light in your head that how it is coming plus 10, because this is wrong. Because you cannot have plus 10 oxidation state. See, the highest oxidation state or oxidation number, whatever you call, ever achieved is plus 8. In a negative, it is a minus 7, and in a positive, it is plus 8. And that too is given by rhenium and osmium. Rhenium, osmium, and in some rare cases, iridium also. So rhenium and osmium. So this is plus 10. That means dal mein kuch kala hai. So this is not plus 10 at all. And see, before checking whether given element's oxidation state is what, you also need to give a check to its electronic configuration. If you look at the electronic configuration of a chromium's atomic number is 24. So its electronic configuration comes out to be chromium 24. You got argon, which is your noble gas core. Argon 4s1 3d5. 4s1 3d5. So argon's electron will never be lost. It will stay as it is. So maximum oxidation state that chromium might or can have is plus 6 by losing all these 6 electrons. So that is the maximum oxidation state chromium can show. But here it's showing plus 10. The question is it really a plus 10? Let's see. Now these are the exceptions where you need to know the structure also. So I'll tell you what the structure of CrO5 is. Cr double bond O, and you have a peroxide linkage here. This is called as a butterfly structure because you can see it appears like a butterfly. This is the neck of butterfly and these two are the wings. Okay, so you can see here chromium is bonded with a 5 oxygen atom, but how many bonds chromium has formed? Let me tell you one more trick to find out the oxidation number. Check how many bonds chromium has formed. Chromium has formed 6 bonds with more electronegative element. Chromium has formed 6 bonds with the more electronegative element, which makes the oxidation number of chromium to be plus 6. Because you got 2 peroxide linkage, O2 2 minus. On this side you have, this side contributes minus 2, this side contributes minus 2, and this doubly bonded oxygen contributes minus 2. So all of this oxygen together contributes minus 2, minus 2, minus 2. It makes minus 6, and that is why chromium has the oxidation state plus 6. Okay, that is how the exceptions are. Now next, bluely colored sulfur, H2SO5. Now if you find out the oxidation state of H2SO5 here, it comes out something like this. Plus 2 for the 2 hydrogen, sulfur is X, and 5 oxygen atoms, right? Each oxygen atom is minus 2. The 5 become minus 10, right? Let's make it faster now. Overall charge is 0. So plus 2 minus 10, it becomes minus 8. X minus 8, 0. Therefore, X is equal to plus 8. Again, you cannot have sulfur in the oxidation state as sulfur 8. Why? Because again, atomic number of sulfur is 16 its electronic configuration becomes neon 3s2 3p4. So after noble gas core, you have 6 electrons in the sulfur. The sulfur can lose maximum 6 electron, and it can have maximum plus 6 oxidation state and minimum minus 2. Okay, so it goes from minus 2 to plus 6. But here we are seeing that sulfur is having a plus 8 oxidation state. That means again there must be some anomaly here. And yes, there is an analogy. There is an anomaly here. What is that anomaly? The sulfur H2SO5 is also called as peroxymonosulfuric acid. Peroxymonosulfuric acid, that means you have a structure like S double bond O, S double bond O. You have a OH on this side, but on this side you have a OH. And this linkage is called as peroxy linkage. This linkage is called as peroxy linkage. So if you look at it, as I told you in the case of chromium, look at the sulfur. How many bonds it actually has formed with the oxygen? It has not formed a 7 bond. If you look at the sulfur, double bond here, double bond here, single bond here, single bond here. So basically your sulfur has formed 6 bonds, which makes its oxidation state plus 6, and it is plus 6. Okay, that is how these anomalies are. Okay, you need to remember some of these anomalies. Okay, I would call it as anomaly as such. It's because you should know the technical background, or you should also know the basic of the given oxidation number. You should always find a reason that why this element cannot have a particular oxidation number. Okay, from that you should know its atomic number, its electronic configuration. Okay, if you know that, electronic configuration is one of the most basic thing. Like, we haven't seen that chapter, that is the periodicity. Okay, when we will cover that, you will understand all these things. Okay, sure. Moving ahead. Next, paradox. Paradox of fractional oxidation number. So what is this paradox? See, C3O2. Now we're going to solve here the red colored elements oxidation number. So if you find out C3O2, if you find out its oxidation number, it has to be 3x for 3 carbon and 2 oxygen, each in the minus 2, 2 in the minus 4 is equal to 0. So 3x minus 4 is equal to 0. Therefore 3x is equal to 4, and therefore x is equal to 4 by 3. That means each oxidation number, each carbon is in the plus 1.33 oxidation state. Now that is not a fact. You know that carbon cannot exist in that oxidation state. So what is the structure? Structure of C3O2 is this: C double bond C, double bond C, double bond O, double bond O. This is called as carbon sesquioxide. Sesquioxide. Okay, it is a name given to it. Okay, so that sesquioxide doesn't have something connected with this, but this is how the structure is. So you can see this carbon is in a plus 2 oxidation number. This carbon is in a plus 2 oxidation number. This carbon is in a 0 oxidation. So if you add them together, you will get the plus 2, 0, plus 2, which makes it plus 4. And since you got 3 carbon atom, the plus 4 divided by 3, it becomes plus 4 by 3. That is how this fractional oxidation number comes out to be. Okay. Then Br3OH. Again, Br3OH, if you find this out, for 3 bromium, it becomes 3x. 8 oxygen, that means minus 2 into 8. It becomes what? Minus 16. 0. 3x is equal to 16. Therefore, x is equal to 16 by 3. Okay, that is how your Br3OH is. But is it the real structure of Br3OH? No, it is not like that. Let's see how its structure is. You got 8 oxygen atoms. You got double bond O, double bond O, double bond O, double bond O. Okay, again double bond O, double bond O, like this. Br3, now this is attached to another bromine, like this. 6 6, yeah, double bond O, double bond. So if you look at this bromine, I'm talking about the terminal bromines. So this right side wala terminal bromine is attached to 3 oxygen atom via 6 bonds, right? So basically it has formed 6 bond with the oxygen atoms. So it's, and from the one side it is attached to another bromine, to which its electronegativity difference is 0, right? That means this bromine will have oxidation number +6. Same goes with this left side wala bromine. It also has from 6 bonds with 3 oxygen atom. On the right hand side it is bonded with another bromine. So this is also +6, right? And this central wala bromine has from 4 bond with the 2 oxygen atom, which makes its oxidation number +4. So when you know the structure, you come to know that there is no bromine which is in the fractional oxidation state as such. 2 bromine are in a +6 each and 1 bromine is a +4, which makes it together +16 divided by 3. That is why we are actually finding out the average oxidation number of bromine, but actually it is not. Okay. Next, S4O6. I think this we had seen already, right? There you got S4O6 2 minus. In that case, you got 2 sodium. फिर भी, let's find it out. Again, 4x minus 12, right? 6 oxygen atom, no? Each is in the -2. 4x minus 12 is equal to -2 charge, because this is not neutral. The charge actually is 2 minus, okay? So 4x is equal to -2 plus 12. So 4x is equal to 10, and therefore x is equal to 10 divided by 4, which is equal to 2.5. Remember, we had seen this earlier. So how the structure is? We had seen that also. S double bond O, S double bond O, O minus. You got sulfur, sulfur. S double bond O, S double bond O, O minus. So this sulfur is in a +5 oxidation state. This sulfur is in a +5 oxidation state. This sulfur is in a 0, 0. That makes the whole average 10 divided by 4, and that is why you have 2.5 as an answer. Okay. That's it for the paradox of a fractional oxidation number. Okay. Moving ahead. Now, what are oxidizing agent and reducing agents? Oxidizing agents and reducing agents. See, oxidizing agents are those compounds which can oxidize others. Oxidizing agents are the compounds which are oxidizing another compound. Now, when you're oxidizing another compound, they are getting reduced themselves. So, oxidizing agents are those compounds which can oxidize others and reduce itself during the chemical reaction. And those reagents are those reagents whose oxidation number decreases. Now, obviously, if you're oxidizing someone else, you should get reduced. When you are getting reduced, your oxidation number has to decrease. That is why those reagents whose oxidation number decreases or which gains electrons in a redox reaction are termed as oxidants. Again, oxidizing agents are those compounds which can oxidize others, themselves getting reduced during the chemical reaction, or these are the reagents whose oxidation number decreases or they gain the electrons in a redox chemical reaction. These agents are called as oxidizing agents or oxidant. Okay, what are some of the powerful oxidizing agents? The example which I am giving you here are the powerful oxidizing agents. Of them is KMnO4. KMnO4 is also called as a Potassium permanganate. You should know the name also. Potassium, K stands for potassium, potassium permanganate. K2Cl2O7 is potassium dichromate. These are one of the very strong oxidizing agents, okay? Both KMnO4 and K2Cl2O7. Then you have a HNO3, nitric acid, and then you have a sulfuric acid, H2SO4, which everyone is known with already, right? These are some of the stronger oxidizing agents. Now, reducing agents. What are reducing agents? Now, you are already known with what oxidizing agents are, right? That means reducing agents are something which are exactly opposite to reducing oxidizing agent. So reducing agents are those compounds which can reduce others. Reducing agents are those compounds which can reduce others and oxidize themselves. So reducing agents are those compounds which can reduce others and oxidize itself during chemical reaction. Those reagents, or in oxidizing agent case, you know that oxidation number was decreasing. In this case, it's increasing. So, and those reagents whose oxidation number increases or which loses electron. Now, obviously, if you are reducing someone, you has to get oxidized. If you are getting oxidized, that means your oxidation number will increase or you will lose electrons in a redox reaction. These are called as reducing agents or reductant. Okay. What are some of the powerful reducing agents? The Ki, Na2H2O3, sodium thiosulfate, HI is also there. HI is a powerful reducing agent. Then you also have a hydrogen gas. So these are some of the powerful reducing agents. Okay. And then there are some compounds which can work both as oxidizing agent as well as reducing agent. The prime example of them being H2O2, hydrogen peroxide. Hydrogen peroxide is one of those compounds which can act both as oxidizing as well as reducing agent, and you also have NO2 1 minus nitric compound. This compound can also act used as a both oxidizing as well as reducing agent. Okay, chalo move ahead. Yeah, so how can we find out whether given compound is oxidizing agent or reducing agent? Then there is a chart for it. First of all, find the oxidation state of central atom. First of all, find the oxidation state of a central atom. Central atom means suppose you have a compound called HClO4 like this. So let's take what is the central atom here? Central atom is chlorine. So what is the oxidation state of central atom? HClO4 chlorine. If its OS is maximum, then it must be oxidizing agent. So if you are talking about HClO4, the +7 is the oxidation state of chlorine. +7 is the oxidation state of chlorine, and it is its maximum oxidation state, which makes HClO4 an oxidizing agent. Similarly, again, find the oxidation state of central atom. If the OS is equal to minimum OS, if its oxidation number is minimum, then it can act as a reducing agent. It can act as a reducing agent. For example, HI. Now, HI central atom actually is iodine. Now, iodine's oxidation number is -1 here. Now, -1 is its minimum oxidation state. That means your HI can act as a reducing agent. That is why I am saying this. So this is a simple trick. Find out the oxidation state of a central atom. If that oxidation state is a maximum for that central atom, then that compound can act as the oxidizing agent. If that oxidation state of that central atom is its minimum oxidation state, then it can act as a reducing agent. And if the oxidation state is in between, then it can act as a both oxidizing agent or reducing agent, or it can disproportionate, or it can disproportionate. We will see that how it can disproportionate, okay, but that is in the next chapter. Okay, so moving ahead. Now, oxidizing agent, reducing agent. Now, what is redox reaction? The name of our chapter. What is a redox reaction? See, a reaction in which oxidation and reduction happens simultaneously. A reaction in which oxidation and reduction happen simultaneously are called as redox reaction. So in all redox reaction, the total one, you need to remember one more thing. Oxidation reduction has to happen simultaneously. Then only you can call a given reaction as redox. Secondly, in all redox reaction, the total increase in oxidation number, must be equal to total decrease in oxidation number. That means whatever species are undergoing increase in oxidation number, the other species must be showing some same number of decrease in oxidation number. Then and then only you can call that as redox reaction only. For example, I have brought an example for you here. See, the oxidation state of iron here is +2. It's +2. If you go by here, you can see iron has been converted into Fe2SO43. Now Fe2SO43, the charge of SO4 is -3, sorry, -2. -2 into 3 become -6. Now 2 Fe are distributing -6, that means they must be having a +6, and each Fe will have a +3. So 5, not 5 actually, 10 iron atoms from +2 they went to +3, right? So if you take the single Fe atom, single Fe went from +2 to Fe +3, but you got a 10 Fe atom, no? So total loss of electron, I would say increase in OS, rather you can say the increase in OS. The increase in OS for Fe is equal to 10. Now you can see increase in Fe for iron is 10, then there must be decrease in Fe of some another atom, and it has to be equal to 10. Then and then only you can call this as redox reaction. Let's look at it here. The manganese. Oxidation state of manganese is how much here? It's +7. Remember, we found it earlier. It's +7 here, and here manganese is in the +2. So one manganese went from +7 to +2. That means it has been showing decrease in OS. So decrease in OS here is how much? Decrease in OS for each manganese atom is equal to how much? 5, right? It's 5. But you got 2 manganese atom, no? You got 2 manganese atom here. So each manganese atom is 5 into 2 is equal to 10. So decrease in OS is shown by manganese, that is 10, and increase in OS is shown by Fe, which is also 10. That means both of them are equal, and that means this reaction is redox reactions. So that is the way you can find out whether given reaction is redox reaction or not. Okay, so moving ahead. Now let's see one numerical. The incorrect order of decrease in oxidation number of sulfur in compounds is. So that means what they are saying, the oxidation number of sulfur has been shown in a decreasing way. Which order is incorrect? Okay, now Let's solve it one by one. So if you look at the first example, sulfur is in zero oxidation state here. Here 3 oxygen minus 6, right? 2 sodium minus 6 plus 2 plus 4 plus 4 divided by 2 plus 2. Sulfur is in a plus 2 here. Here 6 oxygen, 6 into 2 minus 12, right? Minus 12 plus you got 2 sodium, minus 12 plus 2 sodium plus 10 plus 10 divided by 4 plus 2.5. And here sulfur is in a 7 into 2 minus 14 minus 14 plus 2 plus 12 plus 12 by 2 plus 6. So this is the right oxidation. This is the right order. This is not incorrect. Incorrect one. Here sulfur is in a plus 6. Here sulfur is in a plus 4. Here is in a plus 2. Here sulfur is in the minus 2. This is also correct. Incorrect order. Here sulfur is in a plus 6, plus 4, minus 2, and 0. This has to be wrong, right? Because minus 2 has to come last. I said 0 has to come first. So it has to be plus 6, plus 4, 0, and then minus 2. That means this is the wrong option. That is our answer. That is our answer here. Next. In which of the following reaction is there a change in oxidation number of nitrogen atom? That means which species is showing change in oxidation number for nitrogen? Let's look at the first. Nitrogen here is in a plus 4 oxidation state. Why? Each oxygen is minus 2, 2 oxygen minus 4. So nitrogen will have a plus 4. Look at here. Oxygen is in minus 2 into 4 minus 8. Minus 8, that means nitrogen will be in the plus 8. But 2 nitrogen atom plus 8 divided by 2 plus 4. So there is no change in oxidation state here. Okay, they have asked us to find out the species showing change in oxidation number of nitrogen atoms. Okay, nitrogen here. Here nitrogen's oxidation state is minus 3. We had seen that. And NH4 plus OH. NH4 plus OH minus. If you find out the nitrogen's oxidation state in NH4 plus, you can see it is we don't know. So nitrogen X, 4 nitrogen atom, it becomes plus 4 is equal to plus 1. So X is equal to plus 1 minus 4. X is equal to minus 3. So nitrogen oxidation state is here also minus 3. There is no change in oxidation state. Again N2O5. In N2O5, 5 oxygen atoms are there. Minus 5 into 2, minus 10. Minus 10, that means nitrogen will be in the plus 10. Plus 10 divided by 2, it is in the plus 5 oxidation state. And in HNO3, you can clearly see nitrogen is in a plus 5 oxidation state. So there is no example where there is a change in oxidation number of nitrogen atoms here. In every species, the left hand side and right hand side, both the nitrogen atom has a same oxidation state. That is why the answer of this question is none. It is none. Okay, there is no species which is showing change in oxidation state of a nitrogen here. Okay, and that is it for today. So we have covered the first part of our redox reaction chapter. In the next lecture, we will see how to balance the chemical reactions by using oxidation and reduction terms. Okay, that's it for today. Bye bye everyone. Good night.